Okay, now let's little bit talk about native and pseudo load store. Sometime assembler rearrange the memory access instruction as needed in case of displacement addressing because of it cannot reach the requested address. Okay, so load word store word, like you will see different variants you can use in the in the program in the MIPS environment, and not all of them would look uh, like an like a native load word store word. Like native load word store word is always displacement address, means you are defining a base register and then defining an offset, and then that's the address you are looking for to operate, right? Mars, it can actually you can uh, like refer to an label that okay, go and read from that label or load word from that label, like the address pointed by the label calculated in the symbol table, or like store it there and so on and so forth. So those all everything else, if you use them other than the displacement format that I have shown you in the previous two slides, they are all pseudo instruction. Okay, let's do it with an example program, right? Let's do it in an example program. Let's open up the Mars and let's load a program. Okay, okay, let's see. Teaching. So it is an experiment 9. Okay, so here is your experiment, right? So it's a very simple program. We are trying our load word store word. Okay, some T0, some value we want to load from this area, like this GP global pointer minus some value, and GP plus some value, like positive and negative addresses. I've given some address calculation like hints what is going to be, and then another a little different value. It is 8000, and in this case now next case is 8004, and this is like little bit beyond 8004, and for example load word here is the example I was giving, like instead of doing this kind of, this is looks like an these are all your native instructions, at least it looks like by the format, but this one is not like the format. We are using directly a label. The label is being here, right? So what all we are trying to do is load word from the address that is computed for STR. Okay, so let's assemble this program. Now what happens, this STR, as this program says, first of all look at this dot data followed by an address. So we are forcing the data start address from next successive labels would be, or not next successive label, like theoretically speaking it is next successive data allocation that we do, like a dot ASCII or dot byte or dot word. They don't necessarily actually go through like start with a label, like we can just lay it down without a label or without a name, but they will start laying down this data from this location 10000000, which is like starting the base address of the static data. Okay, so your STR start from there. Okay, but here your base address Mars start from, by default start from 1001 0000. I think that is also one difference than what MIPS says to start the data from. Okay, so so we go for here, right? So I think what is happening, okay, let me, before explaining anything, let me tell you something. Like dot data, MIPS suggests to start from this guy, okay, but Mars start from 10010000, and your heap start from 10040000. Okay, so heap is starting from quite a bit higher than what MIPS suggested, and your dot data, anything goes in the dot data goes from starting from this address. Okay, only the external and global variables goes into your, like you can define it in your dot data section, but if they are global, then it will go in starting from the base address that MIPS suggests to do it as a static data. Okay, so that's one thing to note. So that's what we are forcing here as an assembler. We are forcing it to start from really MIPS suggested base address. Okay, that's what we are doing here. Next thing, this is my string. From that location, I can actually change any part and see what's going on at that location. That is one new thing. Probably, if you haven't explored, please explore this part as well. Your str start at this address. Your main start at 00400000. That's what your program counter is also initialized. Okay, now here look at this source code. First to load word, store word is the same thing. Like it's just your basic become like this, almost same thing. Like okay, GP is $28 and T0 is $8, and this is your sign extended hex. Okay, minus 80000. I want to treat it this is like a 16-bit, but what I'm telling assembler, treat that as a negative value. Okay, so that's what you're giving, that negative value, and we have another positive value here. But look for the next one. I have said on minus 8004 GP, and that expanded as 3 instruction, not just 1 instruction. It involves a Louis, and then add some, like add into that 80 register, like you load upper immediate this all F, and then you basically add the content of 28 register onto it, and then you use 80 as your base address with some offset. So with these 3 operations, what assembler tried to do is to follow my intention that okay, have an offset from GP register going this much negative amount. Okay, 8004 negative amount. Why it could not do it in 1 instruction? Because remember, if it is the native instruction load word, the offset must be 16-bit, but minus 8004 cannot be represented in a 16-bit 2's complement format. Its range does not allow, it's beyond the range. So that's why your assembler tried to get around and kind of treat this as a pseudo instruction and expand that into multiple operations, so that at the end of these 3 successive instructions from Louis, add U, and LW for line 18 of the source code, they perform the equivalent same operation on the same memory address. So through all this transformation, it just wanted to make sure whatever memory calculation you are doing at the LW instruction at address 40010, it's equivalent to what you intended to do at line 18 of your source code. Same goes with the store word. Now it's a little bit differently expanded than the load word. It was using Louis. It is now doing some ORI and doing some addu there and then store word. But nonetheless, it's kind of an address manipulation it wants to go for. That at the end of the day, the store word at this position 40001C, that address computed as the same address what you intended in line 22 of your program. Though this 8004 is beyond your 16-bit 2's complement value range. You cannot put directly into the machine code. So this store word will be treated as a pseudo instruction. Okay. And last but not the least, look at this load word T0str, which is straightforward. We can say that this is pseudo instruction because basic load word store word is always displacement format. You define a base register, you define offset, and you access it, right? But from the code 24, it looks like we are just referencing to a label. So it expanded in certain way so that we can ultimately use an basic displacement based load word, and it involved two instructions in this case, Louis and LW, and at the end of the day it made sure that 400024, that memory address calculation will become your address of the STR, which is like this value. Like you can look at the label table, it is kind of a symbol table for you. It's with a more like an address calculation for the whole thing. So that's, I think, experiment 9. So what all we try to establish is that from code wise it may look like a native instruction, but we really need to do some deep analysis onto this offset value, especially with the offset value, to check if it is really a basic instruction will be used in the assembling, or it will be replaced as a pseudo instructions and replaced with some like two or more basic instruction to achieve the same goal.